we have seen about this type 2 type of solid solutions, wherein the two metals were completely soluble. Okay, two metals were completely soluble in the liquid, but insoluble in the solid state. So when it is completely soluble in the solid state, and when it is completely soluble in the liquid state but insoluble in the solid state means, so when you increase the temperature and when you increase the composition of one percentage of B with respect to the another, the how it behaves, okay, how it behaves, this part will be having a solid A plus solid B. Okay, last class itself we have discussed about it, and the remaining this half of, as this is the eutectic point, number 4 is the eutectic point. Here it will be solid A plus eutectic mixture, and here it will be solid B plus eutectic mixture. And this part, the above part, above this eutectic line, you will be having the liquid, and this portion below the curve, we call it as liquid plus solid A and liquid plus solid B. Okay, so these things we have seen in the last class itself, and these are from the from what you can say, from the curve we can also find the percentage, that A percentage is nothing but X2L2 by T2L2. T2 X2L2 is nothing but, see here, X2 is this X2L2 by T2L2. T2 is where? T2L2. So X2 plus L2, this whole, okay, this distance by the whole distance, T2L2 will be giving you the A percentage. Okay, will be giving you the A percentage. Then the reverse will be the L2 percentage. Okay, so L2 percentage is this, the whole liquid, and this is the A percentage. So that A percentage and the L percentage can be calculated at any point. Okay, so these things also we have seen when it is solidified, how it changes. Okay, how that eutectic and the primary mixture. Okay, initially it will be in the solid, then some part of solid will become, the grains will become the grains will be reduced in size, the grain size will be reduced, and then when it converts into liquid medium, your eutectic mixture will be formed. Okay, which will be a combination of solid A and solid B. Okay, those things we have up to, those things we have seen. And when the percentage, okay, when the percentage decreases, when the percentage, here if you see, it is completely aluminum only, but slowly we are adding silicon. Okay, in alloy 2, if you see, 2.8 percentage of silicon we have added, then 12, 20, 50, and almost pure silicon. Okay, so when it is a pure aluminum or a, sorry, yeah, when it is a pure aluminum or a pure silicon, you will be having only a mixture, not a mixture, only a particular element in it. Okay, but when you start adding another component here, a mixture will be starting to form. Okay, that is, with the eutectic mixture will be formed, with the primary silicon content is continuously increasing. Okay, increasing. So when the silicon content is more, automatically the aluminum silicon intermetallic compound will be formed. Okay, so that compound which is formed only from 20% silica, here, and 12% silica also it is seen, but it is very smaller. Okay, whatever you are seeing is very smaller, but when you go further with the increase in the amount of silicons, that silicon intermetallic compound formation is comparatively higher. If you can see, this black color portions are comparatively higher in the higher amount of silicon. Okay, are you listening? Are you following? Hello, hello, are you there?
Yes, sir. Yes, sir.
Yeah, good. Okay, so it is going like that. Okay, so now when you go for with these things and all, we have seen all the last class itself, and this mixture also we have seen. Okay, two metals, but only partly the type 3. Okay, till now we have seen the type 2. This type 3 only now we are going to see. Just a minute. Yeah. Yeah. Yeah, type 3 is nothing but two metals completely soluble in liquid state, but only partly soluble in the solid state. Okay, so when it is partly soluble in the solid state, you will be having another phase here. Okay, there in the previous phase, we had only solid A plus solid B above the eutectic point. Below the eutectic point, we had only solid A and solid B. Now they told partly soluble. Partly soluble means some liquid content will be there. Okay, some liquid content will be there, so this liquid plus mixture will be dragged down also. Okay, will be dragged down also, so it will be forming two phases, the solid, the alloy which is mixing, will be forming two phases. This will be one phase and this will be another phase. Here you will be having that alpha plus beta. And below that eutectic point, this region will be alpha plus eutectic mixture, and this region will be beta plus eutectic mixture. But when you see above this eutectic line, already there is one phase. Okay, we call it as beta phase. Okay, beta phase, and here pure beta phase. Here it is pure beta phase, and here it is pure alpha phase. So below the eutectic point, you will be getting that alpha plus beta phase, and that if you draw a line from the eutectic point, it can be divided into two halves. Now this region will be liquid plus alpha, and here it will be liquid plus beta. But above it fully it will be a liquid. So at different compositions, for example, if you take at 5 composition of the particular B, a 5-8 percentage of the B element, it will be forming the alloy 1. Okay, at 5 percentage it will be forming alloy 1. It may be having some properties. Okay, it may be having some properties, but it will be meeting at the region, the curves, the solidus liquidus line. It will be meeting at the point T1 and T4. Okay, it will be meeting at the point T1 and T4, wherein the gap will be here. But when you take this alloy 2 here, this alloy 2 will be meeting the line at the eutectic point E. Okay, at the eutectic point it will be meeting, but the percentage of weight percentage will be 70. Okay, the remaining other element will be 30. Okay, just a minute. Okay, so that alloy 2 will be meeting at the point E, and here the temperature transmission region will be at both the temperature transmission region and the solidus line will be intersecting at the point E. Okay, but here if you take alloy 3, alloy 4 and all with different weight percentage, it will be passing through different points. Okay, so this is what the phase diagram of this what you can say, this two metals which are completely soluble in liquid state but partly soluble in solid state. So at what temperature, how it will behave? Okay. For example, if you take the temperature TE and if you take 40 percentage of weight, so at that point, how it will be? For example, if you take a temperature here, okay, if you want to meet at 40 percentage of B, it will be having both alpha plus beta phase, but alpha plus eutectic mixture will be there. Okay. So this is what about two metals which are completely soluble in liquid state, but only partly soluble in the solid state. So now if you take this diagram, as I told, this diagram will show you wherein we have drawn the series of cooling curves. Okay, as I already told, this phase diagram is nothing but the combination of series of cooling curves which are joined together to form that region. Okay, that region. So now how it behaves? Initially, when it is higher temperature, when the temperature increase, the solid will be forming to a complete liquid solution. Okay, so first it will be an alpha solid solution. We call it as 5B, where it will be fully solid. And when we include a liquid mixture, an alpha combination will be there. An alpha solid will be there, and also a liquid solution also will be there. When you still increase the temperature, it will become a liquid form. Okay, it will become a liquid form. So this is the series of cooling curves. Okay, this is the cutting region, and a series of cooling curves will be there. See here, alloys in the system never solidify as the crystal in pure A and pure B, but always a solid or a mixture of solution will be there. Either it will be a alpha phase or a beta phase solid solution. We call it as the terminal solid solution. These types we call it as the terminal solid solution. And 30A, for example, if you take this point, the point where it is meeting. So at 30A and 70B, I already told you here 70. At 70B, 70B means automatically it is 30A. 30A, it is the eutectic composition. Eutectic it is composition. For example, if you take this 5B, and 95A, means it will be 90. 95A, 95A means automatically it is 90A. 90A, it is 90A. 90A, it is the eutectic composition. Okay, so this is what about two metals which are completely soluble in liquid state, but partly soluble in solid state. So now how it behaves? Initially, when it is higher temperature, it will be meeting at 40 percentage of weight. So at 40 percentage of weight, when it is higher temperature, the solid will be forming to a complete liquid solution. Okay, so this is what about two metals which are completely soluble in liquid state, but partly soluble in solid state. So now how it behaves? When it is higher temperature, it will be meeting at 40 percentage of weight. So at 40 percentage of weight, when it is higher temperature, the solid will be forming to a complete liquid solution. Okay, so this is what about two metals which are completely soluble in liquid state, but partly soluble in solid state. So now how it behaves? Initially, when it is higher temperature, it will be meeting at 40 percentage of weight. So at 40 percentage of weight, when it Type 1 means this one phase, this type 1 phase. Okay. So these are the various notations in which the solidification of an alloy can be categorized. Okay. So by the how much percent, how much alpha is there, how much beta is there, how much is there can be calculated at eutectic temperature or at the room temperature. For example, at eutectic temperature, if you take, it will be Eg. Okay, this is beta, right? Alpha. Okay, Eg by Fg is the total thing. Okay. Okay, Fg is the total. Okay, Fg is the total. So this Eg by Fg total will be give you 1%. Okay, that will be the alpha percent. The remaining is Ef by Fg will be giving you the beta percent. Similarly, if you take at room temperature means ordinary temperature here, baseline, Kj by Hj or Hk by Hj. Okay, so that will be giving you the corresponding percentage within that region, within the solubility or the characteristic or the study region. Okay, usually when you take this microstructure of these kind of alloys, it will be having both pro-eutectic, it will be having, that is vacuum, we call it as vacuole regions. Okay, these regions also will be available, and the eutectic mixture region will be also available. Primary alpha also will be there, and alpha plus beta also will be available there. Okay, so these are the type 3. Okay, this is the same diagram that we have seen here, how it will be changing. That is, initially alpha solid will be there as a small particles. Okay, as a small particles in the eutectic point. In this point, if you see, it will be that solids will combine. The solids will combine and form a bigger solid, and still more it will combine, and then only it can form a full solid. Okay, or you can see it or study it in the reverse way also. Okay, these are the same things as I told. Okay. Yeah, these are the structures. These are the structures. Alloy 1, alloy 2, alloy 3, and all I told you, right? The different alloys, where it is. Yeah. Alloy 1, alloy 2, alloy 3, alloy 4. And these structures, okay, these are the microstructure or the anatomy of those different alloys. Okay, the different alloys are the equilibrium wherein the particular percentage of that uh, uh, antimony will be there and lead also will be there. Okay, so these are the various combinations. Okay, the same thing. Okay. Now, when you talk about the properties of this eutectic alloy, one phase will be relatively weak. Okay, one phase will be relatively weak and plastic. Okay, one phase. Okay, we are taking two phases, right? Out of that, one phase will be relatively weak and plastic, while the other phase will be comparatively hard and brittle. Okay, therefore this kind of system, the eutectic composition will be giving you the maximum strength. That is the composition 70 by 30. I told you, right? 70% B and 30% A. That 70 by 30 will be giving you a comparatively a maximum strength. And in these compounds, if you do age hardening means is nothing but the heat treatment process of these non-ferrous alloys. Okay, if you do age hardenings, the equilibrium diagram will be showing you some partial solubility. There will be higher solubility at higher temperature than at the lower temperature. Okay, so these things will be usually satisfied with alloy 4 only, alloy 4 of type 3. Where it is alloy 4? If you see alloy 4, it is here, 15 percentage of B and 18 percentage of 85 percentage of A. Okay, so these are the things. Okay, now this is the aging process. After aging process, what it will happen? Similar alloy, after slow cooling, it will be like this. Okay, so initially it will be heated to a particular temperature. Then after cooling, it will be like this. Okay, it will be separate alpha beta particles. Somewhere it will be as like a grains. Okay, it will be like a linked format. Okay, beta particles will be linked somewhere, and that linked format will be forming the grains after reheating and rapid cooling at the room temperature. It will be forming a grains. Okay, all this chain of beta particles. Okay, the chain of beta particles will combine together and form the grain, and in between the grains you will be having the alpha particles. That alpha particles will be breaking and breaking and breaking, and it will be aged. Okay, after aging it will become a very small grain size, and it will become alpha beta will become smaller grains, and it will be embedded within the grains. Okay, within the grain boundaries. Okay, within the grain boundaries. Okay, this is very important. Okay, so when you do this kind of aging, automatically the hardness value also will be increased. Okay, the hardness value also will be increasing to a considerable extent, and then it will be up to a particular time. Up to a particular time, if you do aging only, it will be having a good proportionate. Okay, it will be good proportionate at different temperatures. Okay, at different temperatures. Okay, it may vary. It may vary. Okay. Next, type 4. Type 4 is nothing but a congruent melting intermediate phase. That is, as I told, when we are changing one phase to another phase without any change in the chemical composition, there will be a extra intermetallic phases will be formed. Okay, intermetallic phases will be formed, and that compound we call it as intermediate phases, because the single phase that occurs, okay, between that two phases, okay, already we are adding two phases, and between that two phases and another phase will be formed. Okay, between the two phases and another phase will be formed. So when this another phase is formed, automatically, listen carefully, automatically an intermediate phase will be formed, but that intermediate phase will be formed only in a narrow range of composition, only in at a particular range, only if this B is at a particular range and A is at a particular range, only for that particular range of composition, that intermediate phase will be formed. That intermediate phase can be labeled, and it can be denoted as a vertical line also in this phase diagram. In some cases, that compound, that intermediate phase compound will be an advantage. In some cases, it will be a, okay. Now see here this is a melting point of A, okay, melting point of A, and this is a melting point of B. Intermediately, in between both the melting points, you will be having the melting point of that intermetallic compound AMBN. It may be of any valency, okay, AMBN. When one phase changes into another phase isothermally without any change in chemical composition, it is termed as concurrent phase change. Okay, that is intermediate formation, intermetallic compound formation. Okay, concurrent phase change or concurrent transformation. Okay, so these are the things. See here the A will be there, here A will be there, and where alpha will be there, and this is the A and B, an intermetallic compound A and B, and will be formed, and below this side of this will be alpha plus A and B, and above, you know, this is a eutectic point, above it is liquid. For here, for this alpha, here it is the eutectic point, so liquid plus A and Bm, here it is alpha, here it is liquid plus alpha, and above it is liquid. Okay, similarly here the eutectic point is here. Okay, two metallic compounds are there, right? Here the metallic compound is here, so A and Bn plus beta. Already this is the intermediate, two intermediate phase will be there, beta. So L plus beta, L plus this A and B, AMBN. Okay, here it will be again liquid. Okay, so these are the phase diagram showing the intermediate phase of AMBN. Here, so liquid plus solid, if you heat it or cool it, a new solid and another intermetallic solid will be formed. Okay, and another intermetallic solid will be formed. Okay, here this is another type, pretectic form of pretectic, some more advanced form of pretectic form of reaction. That is, in the pretectic form, it is nothing but the reverse of eutectic form, wherein the liquidous line and the solidus line will not meet at the same point. You will be having two eutectic points, so as to say, like a point D and a point E. Okay, point D and point E. So the region TA, D, E, and TB. Okay, this region we call it as the liquidus line. So the reason why all the portion above it is a completely a liquid. But solidus line is, it will start from TA, TP, G, J, okay, J, T, E, where it is T. Here J, T, E, and TB. Okay, on TB here, or you can put it as B also. So this region only will be the, okay, this region only will be the solid region. This portion, this bottom portion. Okay, here. But in here it is liquid. This portion is liquid, but the in between will be a solid plus liquid mixture. Okay, solid plus liquid mixture. But you will be having 2 points, D and here. The pretectic point reaction, we call it at happens at point D. Eutectic happens at the point E. Okay, so these are the various phases, how it will behave. Okay, how it will behave when it is heated. That is, as I told you, inconcurrent melting will be happening and intermetallic alloy will be formed. The closer the alloy, the composition, the lesser the A percentage will be. Okay, as you go close to this melting point of A, point A line, ultimately the composition, the chemical composition of A will be comparatively reduced. Okay, that's what we call this as a liquid solution. And when it is mixed with another solid, small solids will be mixed, and the intermetallic compound, see here, A, M, B, N will be formed. Not only that A and B, Like for example, if you mix aluminum and carbon, an aluminum carbonate Al4C3 will be formed, carbide, so as to say. Okay, like that. Okay, so these are the things. So as I told, the percentage, the liquid solid percentage also can be found out by using the equations. Okay, equations. These are the pre-tactic reaction and how the phase will be changing. Okay, how the phase will be changing. Initially, it will be a completely a liquid solution. Then after when it is cooled, it will become a liquid plus solid. So 87-12, then 50-50, then 90-10, then 10-90 it will become. Okay, so the percentage will be continuously increasing or decreasing. Okay, this is again the same thing. And last type is two liquids partly soluble in the liquid state, wherein we call it as a monotactic reaction. Okay, so monotactic reaction, and here the problem is we will be facing experimentally difficulties because higher temperatures will prevent the determination of the position. The positions cannot be clearly determined because the temperature will be higher, very higher, since it is a monotechnic reaction, and both the liquid, both the things, both the phases are soluble in the liquid state. It will be facing a variation. Okay, the temperature will be higher and the experimental difficulty also will be there. So when you take one liquid and heat it or cool it, another liquid will be formed, and along with the solid, so that is the big thing here. That is, if you see here, if it is a 80A, a 40A will be there. That is 50%. If you take 17% will be L2 and 33% will be the solid A. Okay, it will be mostly like this. The curve will be like this. Initially, it will be alpha plus L2, and this side it will be alpha plus L1. Here you will be having alpha, and here you will be having beta. Okay, it is L plus L1 plus L2. Okay. So these are the regions. It will be like this. Actually, the base will be like this. Initially, it will be solid A plus solid B, solid A plus liquid B, then liquid A plus solid B, like this. So alpha plus beta, alpha plus liquid 2, liquid 1 plus liquid 2. That will be the difference. Okay, when it is heated. When the okay, out in that aluminum lead alloy system, if you take and if you increase the percentage of lead, and if you increase the temperature also, ultimately these kind of three phases will be obtained. Okay, one will be solid plus solid, that is nothing but alpha plus beta, wherein we call it as solid A plus solid B. Similarly, alpha plus a liquid, solid A plus liquid B, then both the liquids, liquid A plus liquid B. Okay, so these are the various type to what you can say to make it clear to you. If it insoluble in the solid state means it will be like this. Okay, wherein we will be having only eutectic point, eutectoid point. But when eutectic point, when it is partly soluble in the solid state, you will be having a pure alpha phase and a pure beta phase along with it. Okay, along with it you will be having a pure alpha and pure beta, but remaining things are same. But when it is completely soluble in the solid state means the eutectic point will be at the 2 points. Okay, the changes will be there. Okay, changes will be there. So these are the ordinary basic things, that is different types of crystal systems. Okay, different types of crystal systems. Okay, starting from isometric. Isometric is nothing but the cubic system wherein the three axes will be there, and that three axes will determine the lengths of that cube, and mostly all the three axes will be perpendicular. Okay, in tetragonal, if you see, the length will be comparatively equal in length. Okay, length will be higher, and orthorhombic it will be like a rectangular prism. Okay, hexagonal, you know, hexagonal prism. Triclinic will be all the triclinic will be all the three axes will be unequal in length. Okay, unequal in length, but none is perpendicular to the other. If two axes have become perpendicular to each other, then we call it as the monoclinic. And in rhombohedral or trigonal, none of the axes will be perpendicular to one another, but the crystal will have the same size and the shape. Okay, so these are the 7 primitive crystal systems. Okay, and these are some of the examples. Okay, examples of different types of crystal systems, like a diamond. Okay, diamond fullerness. Okay, fullerness is also an alloy of carbon. Okay, so this is another alloy of carbon is graphite, and this is carbon nanotubes, which will be connected in a form of a tube like structure, so which will be behaving like this. Okay, initially in the bottom it will be alpha, then it will be liquid plus alpha mixture, then above it will be a liquid. Okay, above it will be a liquid. Okay, So this is iron nickel equilibrium diagram. Okay, iron nickel ferrous and nickel equilibrium diagram. Whereas this will be atomic percentage of nickel, atomic weight percentage of nickel, and here it will be denoting weight percentage of nickel. So how it will be varying? Okay, when the temperature is changed, where, see, if you can see it here, Fe3Ni is formed. Fe3Ni is nothing but a intermetallic compound. Okay, intermetallic compound. If you see here, FeNi3 is formed. That is when the temperature of nickel is 70, sorry, not the temperature, composition. Okay, the amount of nickel present is 70, and if the temperature is above 300, 200, ultimately definitely this compound will be formed. Okay, so that is the understanding from this phase diagram. Okay, at different compositions and at different temperature, what kind of phase, in what kind of state the compound will be. Okay, in what kind of state or what kind of state the compound will be. Okay, these things I already told you, ordered and disordered pattern arrangement of solid solutions. Okay, where in ordered pattern, if you see, A atoms and B atoms will be orderly arranged. Okay, A atoms and B atoms will be orderly arranged like this. If it is in the next case, it will be disordered. Okay, it will be disordered, not properly arranged. Okay, not properly arranged. Okay, so these are the other things. Okay, these are the A atom, B atom, beta atoms. These are the different schematic diagrams. Okay, ordered solution will be forming a separate phase. Okay, in ordered solution and all, it will not be having any alpha beta region. Okay, and the eutectic point will not be also a single point. At 2 or 3 points it will be meeting. Okay, usually you can take a gold copper equilibrium diagram. So no two phase region will be formed when it is ordered or disordered solution transformation. Okay, this is also an electrical resistivity. Okay, when the atomic percentage of one element, for example gold, is increased, how that electric resistivity will behave. So the same atom, the same compound, when it is quenched or annealed, how it will be behaving. Annealed means disordered phase will be formed, so it will be like this. Electrical resistivity will increase up to the 50 percentage of gold, but but when it is annealed means orderly arrangement. Okay, it will be like a sine wave form. Okay, similarly, this is another type. Okay, copper palladium alloy. Copper palladium alloy. Here also the eutectic point. Even though if you go up to 1000 or 2000 degree Fahrenheit, eutectic point cannot be reached. Okay, eutectic point cannot be reached, and different solid structures, crystal structures will be formed. Example, if you can take it here itself, alpha dash, alpha plus beta, beta plus alpha. Okay, alpha plus liquid, completely liquid phase will be formed. Okay, this is eutectoid mixture. Eutectoid mixture is nothing but when the reaction takes place and which are entirely in the solid state. And the reactions are entirely in a solid state. That is, when the solid is heated, ultimately the output will be solid 1 plus solid 2. Okay, solid 1 plus solid 2, that alpha plus beta. Okay, the solid plus solid mixture, we call it as the eutectoid mixture. Eutectoid mixture. So when it is an alloy, when it is a solid alloy, it will be forming eutectoid mixtures like this. Okay, but after a very high temperature, a very long high temperature only, it will be forming the liquid. It will be forming the liquid. Okay.